Assalamualaikum and hi everyone. This is a video lecture for Chapter 5, DAQ System and Data Interfacing for subject ENT 286, Instrumentation and Measurement. As an introduction, data acquisition is the process of sampling signals that measure real-world physical conditions and converting the resulting sample into digital value that can be manipulated by a computer. Or in more simple definition, DAQ is typically convert analog waveform into digital value for processing. This figure shows the collection of hardware and software components that enables a computer to receive physical signals. The component of data acquisition system include sensor to convert physical parameter to electrical signals, signal conditioning circuitry to convert sensor signal into a form that can be converted to digital value, analog to digital converter to convert condition sensor signal to digital value, and data acquisition applications are usually controlled by software programs developed using various general-purpose programming languages such as Assembly, Basic C, Java, C++, LabVIEW, and Pascal. This figure shows a block diagram of typical computerized data acquisition system with 8 channels for the input signals. Although most transducers produce an analog or voltage, at least after signal conditioning, some transducers produce digital output. These signals do not pass through the analog multiplexer and analog to digital converter, but take a more direct path to the computer, possibly through a digital multiplexer. The computer may be used to control the process either directly with digital signal or with analog signal from digital to analog converter. The computer system most commonly used for data acquisition in experiment are personal computer using the Windows operating system. Sampling rate of over 10 million samples per second are possible, and more than 3,000 separate sensors can be sampled, although not in the same system at the same time. Several major companies supply software and hardware to make a personal computer into a data acquisition system, and some of the hardware is available in low-cost generic form. This figure shows a board designed to plug into an interior bus of personal computer and a shelter box for connecting the transducer used for the experiment. This board not only permits reading the output of various transducers, but also has output for control of the experiment if required. By carefully selecting supplier, integrating the system and software can be seamless, making implementation straightforward. Although some computers used in data acquisition are highly specialized, for example, the engine control computer in an automobile, the computers normally use a quite standard and have the following components: Central Processing Unit, CPU, Program, software, Random Access Memory, RAM, Mass Storage System, Display, User Input Device such as keyboards and mouse, printers, and plotters. CPU operation follow instructions contained in the user-provided program. The CPU also follow instructions from the computer operating system program and from built-in program. Most personal computers have a single central processor, but may have similar processor controlling certain peripheral devices, such as the display or keyboard. However, since there is only one central processor, for the most part, computers execute instructions in a sequential manner. That is, only one instruction can be executed at a time. The program provides a set of instructions that cause a computer to perform a specific function. The program is often known as software to distinguish it from the electronic and mechanical components of the computer, known as hardware. Software may either be written by the user completely, or it may be commercialized software in which the user only specifies certain input. In some cases, and commonly in data acquisition field, the user may combine his or her own programming and commercialized software. The random access memory is a subsystem of the computer that can be stored information temporarily. In particular, install the program instruction and numerical data when the computer is being operated. RAM is made up of purely electronic component with no moving mechanical part, and as a result, it can supply information to the central processor at a very high rate. The information in RAM are readily be changed by the CPU. RAM is volatile, and all stored information is lost when the computer power is interrupted. Consequently, program and data are permanently stored in the mass storage device. There is normally another kind of memory in computer, read-only memory (ROM), used for permanent storage of information required by the computer to operate. The user cannot normally modify information stored in ROM. Mass storage devices are used to store large volumes of information, such as numerical data and programs, in a permanent or semi-permanent form. The most common mass storage device is the hard drive, where information is stored in magnetic form on rotating metal disks. Solid-state drive, SSD, or flash drive, in which information is stored on fixed semiconductor, are now becoming common. However, manufacturers have made the hard drive a moving target by continuously increasing speed, reliability, and capacity. The display or monitor system usually use a liquid crystal display LCD. The display shows the user a limited amount of information, and also used to a similar device is often used to point to region. The display shows the user a limited amount of information and is also used to prompt the user for required input or actions. The most common user input device is the keyboard. The user simply type required information. However, a mouse or a similar device is often used to point to region on the screen to communicate with the computer. Some computers have what are known as touchscreen, in which the user can touch region of the screen to communicate. While numbers used in the everyday world are normally represented in base 10 or decimals, it is far more practical in computer to represent number in base 2 binary. Information in computer is stored in the bistable device called flip-flop, which can have two possible states. One state is defined as on and is assigned a numerical value of 1, and the other state is defined as off and is assigned a numerical value of 0. A series of flip-flops are required to represent a number. For example, the binary number 1001, which corresponds to the decimal number 9, can be represented in computer using 4 flip-flops. Each of these flip-flops represents a bit of the number. The leftmost one in the binary number 1001 is the most significant bit, MSB. and the rightmost one is the less significant bit LSB. It is common in computer to break a long binary number up into segments of 8 bits, which are known as bytes. There is a one-to-one correspondence between binary number and decimal numbers. For example, the 4-bit binary number above can be used to represent the positive decimal integral from 0, represented by 0000, to 15, represented by 1111. The smallest unit in digital signal is the bit, a construction of the more descriptive phase of binary digit. A bit is a single element in digital signal having only two possible states, on indicating 1 or off indicating 0. Bits are organized into larger units called bytes, the basic unit of information in a computer system. A basic byte contains 8 bits. The total amount of information it can convey is 2 power of 8 equal to 256 possible combinations. ASCII, pronounced as ASCII, is American Standard Code for Information Interchange. ASCII is a simple idea of using number to represent text of any character. By assigning a number for each character in the block of text, it will be easily stored in the computer memory. Table 4.1 shows the decimal code that represents each different character. To make a computer into a data acquisition system, several additional components are required. Multiplexers and analog to digital converters are almost always present, and other components are added as required. If it is necessary to take readings of several measurements at precisely the same time, simultaneous samples and whole device or related system are required. If it is necessary to control the experiment or process, the computer must supply output in digital or analog form. If the required control signal is analog, in order to control such components as valve and heater, the computer system digital output must be processed through a digital to analog converter. As mentioned above, most computers perform instructions in a sequential manner. The simplest method to take data is to read the output of the sensor sequentially. In most cases, the computer reads information from the various channels one at a time using a device called a multiplexer. The multiplexer used in this application is essentially an electronic switch. The computer instructs the multiplexer to select a particular channel, and the data are read and processed. The computer then calls the multiplexer to select another channel, and so forth. A mechanical analog to the DAS multiplexer is shown in this slide. The switches in the multiplexer use a data acquisition system, a semiconductor device. Although multiplexers are rather simple devices, they are subject to some error. One of these is crosstalk. Some channel may interfere with the channel being read. This error is normally a precision error. An additional error might occur if the output signal voltage is not exactly the same as the input. That is, the multiplexer alters the signals. The measure of these characteristics is known as transfer accuracy. In the most common situation, an analog multiplexer is used to select an analog signal from the connected transducer and directly or indirectly connect this signal to the analog to digital converter. However, some transducers have a digital output that can be input to the computer directly by passing the multiplexer and the analog to digital converter. To explain the function of the AD converter, it is necessary to describe two distinct methods by which electronic systems process numerical information, analog and digital. Many everyday electronic devices such as radios and audio amplifiers are basically analog devices. Modern computers, on the other hand, are digital devices. If we are trying to represent a value of 5 volt in an analog device, we could, for example, charge a capacitor to 5 volt. In a digital device, 5 volt will be represented by a digital code, a digital binary number such as 0101, which is stored on B-stable flip-flop. The actual digital coding scheme used to represent an analog voltage is well defined in a particular situation, but it's not universal. Most transducers generate an analog output signal. For example, a temperature transducer might generate an output voltage that is proportional to the send temperature. If the temperature were to be varies in continuous manner, the transducer output will show a continuous variations. There are possibly an infinite number of possible output value. The analog to digital converter is the device required in data acquisition system to convert the analog transducer signal into the digital code used by the computer. The digital representation of the value of the transducer output is a code that is related to the analog transducer output but does not describe the output exactly. For example, we could connect the output of the transducer to a relay, which in turn operates a light bulb. If the voltage is less than or equal to 5 volt, the bulb is off. If the transducer output voltage is greater than 5 volt, the bulb is on. The on-off status of the light bulb is a digital code that crudely represents the transducer output. Similarly, the output of the transducer could be represented by two light bulbs. There are four possible states for the pair of the light bulb as shown in the slide. With two light bulbs, the transducer output is now represented more accurately in digital form than with a single light bulb. This light bulb device represents primitive form of analog to digital converter. The single light bulb device is a 1-bit AD converter and the two light bulb device is a 2-bit AD converter. A bit has two possible states, on or off. Inside a computer, flip-flop instead of light bulbs are used to represent this state. Although the circuitry of analog to digital converter can vary widely, from an external performance viewpoint, they can normally be described by three primary characteristics. The first of these is the number of bits used to represent the output. The greater the number of bits, the greater the number of possible output states, and the more accurately the digital output will represent the analog input. The second characteristic is the input range, and the third characteristic is the conversion speed, which is the time it takes to create a digital output after the device is instructed to make a conversion. The input range of an AD converter is the range of analog input voltage over which the converter will produce a representative digital output. Input voltage outside the range will not produce a meaningful digital representation of the input. The input range of AD converter can be classified as unipolar or bipolar. A unipolar converter can only respond to analog input with the same sign. Example of the input range are 0 to 5 volt or 0 to negative 10 volt. Bipolar converters can convert both positive and negative analog input, which plus minus 5 volt or plus minus 10 volt being typical input range. Many computer data acquisition systems offer the user the option of selecting a unipolar or bipolar mode. A conceptually simple type of AD converter, called a unipolar single-slope integrating converter, serves to demonstrate the AD conversion process. In this device, a fixed reference voltage is used to charge an integrator at a constant rate. The integrator output voltage will then increase linearly with time. As shown in slide, a digital clock counter is started at the same time that the charging is began. The integrator output voltage is compared continuously with the analog input voltage using a comparator. When the integrator voltage exceeds the analog input voltage, the digital clock is stopped. The count of the digital clock is the digital output of the AD converter. A block diagram of a single-slope integrating converter is shown in the slide. The FAT is used to zero the integrator at the start of the conversion. Although they demonstrate the principle of AD conversion in a sample manner, RAM-type converters are not commonly used. RAM converters are not as accurate as other types and are relatively slow. DAQ Components Basic AD. There are a number of output codes that are used to represent the digital output of AD converter. Bipolar converter need to represent input with both positive and negative signs. Bipolar converter most frequently use one of two other common codes, 2's complement binary or offset binary. The output binary number may increase with increasing input voltage or decrease with increasing input. Table 4.2 shows the form of the binary number for this code. VRU and VRL represent the upper and lower value of the input range, and VI is the input voltage. Offset binary is just like simple binary except that for bipolar converter. The output code of 0 corresponds to the lower end of the input range instead of an input of 0. This figure gives some formula that can be used to estimate the output of AD converter. The exact operation of the converter may cause the output to differ by 1 bit. We will discuss more regarding the calculation of each formula and how to use it during our lecture. DAQ component practical AD. The most common type of AD converter used in computerized data acquisition system is the successive approximation converter, employs an interval halving technique. In this device, a series of known analog voltage are created and compared to the analog input voltage. In the first trial, a voltage interval of 1/2 the input span is compared with the input voltage. This slide shows a block diagram of successive approximation converter. It consists of a reference source, DAQ, control logic, and output register. Type of practical AD and its advantages is shown in the slide. First type of converter is parallel or flash AD converter. It has faster conversion, can complete algorithm in one step and as fast as 10 nanoseconds. Second type of converter is half flash converter. This converter has two flash converters and able to complete 12-bit conversion in about 100 nanoseconds. And third type of converter is dual slope integration converter. It has been used in digital voltmeter. The most accurate type of AD, noise is averaging out and the conversion time is slower compared to the previous two. This slide shows the block diagram of parallel AD converter. Parallel converter require a large number of components, but modern high component density chip technology has made them practical. Parallel converters are commonly used for applications where 8-bit resolution is adequate. They are also available with 12-bit resolution but at a higher cost. A common AD converter design used in digital voltmeter is the dual slope integrating converter. A block diagram is shown in figure A and the operation is shown graphically in figure B. While in some situations, a data acquisition system is used only to collect data, it is common for the computer to use the accurate result to change some aspect of the measure system. In process plan, this will be a control function. In experiment, it may be a control or it may be a variation of some independent variable of the experimental apparatus. For example, if we are determining the performance of semiconductor device as a function of temperature, the computer may acquire all relevant data, then change the power of a heater to alter the temperature, monitor the temperature until it has stabilized again, and then acquire more data. Most devices used to control a system, such as solenoid, heater, and valve, are analog devices. These devices operate on the basic of an analog input voltage. To operate this device under computer control, the computer digital signal must be converted to analog signal. If the analog device is simply an on-off component, digitally controlled relay can be used. If the analog device requires proportional control, then a digital to analog converter, DAQ converter or DAC is required. Generally, the output electrical power of a AD converter is insufficient to directly operate most control devices such as proportional valve. Consequently, the output of the converter will be used to operate an amplifier which will in turn supply the power for the activate control device. As shown schematically in this slide, the various bits of the digital output signal are used to operate a set of electronic switches. In this schematic diagram, there are 4 bits and 4 switches. The resulting analog output voltage will be proportional to the digital input number. When a DAS uses a multiplexer, the individual channels are not ready at precisely the same time. If the input signals are changing slowly relative to the time it takes to complete all the reading, this is not a problem. In some cases, it is important that all channels be recorded at precisely the same time. To solve this problem, the channels of interest can each be connected to a simultaneous sample and hold subsystem. This figure shows how a simultaneous sample and hold module is added to the DAS. Each of the top 4 channels connect to a samples and hold device. These sample and hold devices are instructed to take a reading simultaneously. However, the data from this channel are not immediately processed. There are many ways in which a generic data acquisition system component are packaged. They are different in system, size, performance, durability, and features. There are a large number of companies marketing data acquisition system and component, and in most cases, selection of equipment will involve significant research and discussion with suppliers representatively. Furthermore, since the field is advancing rapidly, new features will appear frequently. The general configuration for DAQ are internal single board plug-in system, external system, virtual instrument, digital storage oscilloscope, data and data logger. Example of DAQ board is KIT product, National Instruments in NIDAQ, and Agilent. So that's all for chapter 5. Thank you.